Hey, welcome to this episode. We are looking at step-by-step and rule matrices and using transition matrices to produce new steps and step n in a from the state matrix. Okay, so here we've got the initial state matrix is S0. We're showing that it is, highlight that. We're showing that it's 100, 200, and here's our transition matrix that we're using. We're asked to use a recursion relation. So S0 equals the initial state matrix, Sn plus 1. So each subsequent matrix is equal to T times Sn, which is transition times there. So if we take a look at that, we know that if we're going to write it out anyway, SO is equal to 100 and 200, and then Sn plus 1 is equal to transition matrix 0.9, 0.2, 0.1, 0.8 multiplied by Sn. Okay, so we don't need to replace Sn because that is whatever the previous or the current state is. So the current state at the moment is S0, that's where it stays. We're asked to find S1, S2, and S3. Over here on the CAS, I've set up the matrices, so T and S respectively. And if I put in, so what I want to do first is I want it to remember the S, so which it already will, and then I can simply put in T times the answer. So yeah, previous answer there was that, and that gives me the next one. So S1 is equal to 130, 130, and 170. Then the good thing about the setup I've done is I can hit equals the XE again, and that gives me S2. So here's S2, and while we're at it, we can do S3. So you can see there, I've got S2 is 151 and 149, and S3 is 165.7, 134.3. So I've used that recursively. Now it wants us to determine the value of T5. Okay, so T5 is simply our transition matrix to the power of 5. So because it's a square matrix, we can raise that to powers. And we want to raise that to the power of 5. Do that in the CAS fairly straightforward. So if I pop in T, raise that to 5, there's our answer there. So we've got 0.72269, 0.55462, 0.27731, 0.44538 is our T to the power of 5. Part C asks us to use the rule Sn equals, here, C. So we're going to use Sn equals t to the power of n times SO. And this is going to allow us to find the similar to an nth term, so any one of these without having to perform the recurrence. So let's just write that out so it looks nice. So Sn is equal to, so we know what we're looking at, 0.9, 0.2, 0.1, and 0.8. Okay, to the power of n times the initial state matrix, which is 100 and 200. Okay, so there we have that. So then it asks us, right, using that, determine S2, determine S3, and then determine something slightly larger, or a state for more steps down. And we do that over here, so we can now plug this in. I've already got T and S already specified, so for this I can perform T to the power of, so this is going to be equal to, just to make sure we've got one clear demo, this is going to mean that we have T to the power of 2 times SO. Right, so over here, that's what I'm going to put in. T power of 2 times SO is just S over here. Okay, so then that's equal to 151 and 149. And we continue with the next two. So same deal, T to the power of 3 times S, and then T to the power of, lost my last one, 7 times S. That's wrong S. There we go. Okay, so we can see we've got 165.7, 134.3, and then for this one we'll just go to one decimal place, 191.8 and 108.2. Okay. Lastly, by calculating n from using the rule and the n values of 10, 15, 21, 22, show the steady state matrix is close to 200 and 100. Okay, so let's just give ourselves a little bit of room, or I'll cut it off so that we can see a bit. And pop D here. Okay, D. So if we look at it in terms of n being equal to 10, we'll do n 10, 15, n is 21, and n is 22. Okay, so what we want to see is that when we replace n with these numbers, that when we get to particularly 21, 22, that to the nearest whole number, there's no change in state between the two. So you'll see what I mean here, where we go T to the power of 10 times S is 1, so it's rounded all to the nearest whole number, 192 and 108. Go back in, I'm just going to see if I can switch this. So we've got 10, and then we've got 15, and then we get so this is rounded, goes to 200, and 100. Back in here again. Let's get rid of that. Go to 21. We get 200 again, and 100. And last of all, you know what the pattern's going to be, because you can see it already happening. So t to the power of 22, we get 200 and 100. So you can see after we hit 15 and the 15th state, when we round this, we're getting a value for the state matrix of 200 and 100 when we round it to the nearest whole number, and that's continuous as we go. And we could go up to, we could plug in 100 here. Let's just do that for argument's sake. So if we go to 100, there we go. So we hit 100 and it's now rounding completely to the nearest whole number. So that is now proving that our state matrix, the steady state of this matrix, is 200 and 100. Okay, so whatever we do past effectively 15, round to the nearest whole number, these numbers here won't change. So that's our steady state. Okay, hope that's helpful. And if you like it, give it a thumbs up, comment if you've got any questions, and otherwise, we will see you next time.